Okay, continuing on with Chapter 7, this will be Descartes' rule of signs. And this is the way to determine the number of positive zeros and negative zeros in a polynomial f of x. Okay, so it's a little wordy, but it's actually pretty simple once you see the examples. Anyhow, for a polynomial function f of x, the possible number of positive zeros are the number of plus minus sign changes minus an even whole number. Okay, for example, if there are 5 sign changes, then the polynomial has 5, 3, or 1 positive zeros. All right, by sign changes, we mean the plus minus sign. If there are 6 sign changes, then the polynomial has 6, 4, 2, or 0 positive zeros. So basically, we'll get to the examples in a minute, but basically you look at the number of plus minus sign changes, okay? And however many sign changes there are, that's how many possible positive zeros there are minus an even whole number. So if you count 5 plus minus sign changes, you have 5, 3, or 1 positive zeros. If you count 6 of them, you have 6, 4, 2, or 0 positive zeros. All right, again, we'll get to the examples in a moment. Now, for the negative zeros, it's the same thing, with the exception of plugging in negative x in place of x. Okay, so for the polynomial function f of x, the possible number of negative zeros is the number of plus minus sign changes in f of negative x minus an even whole number. In other words, you want to plug in negative x in place of x and then determine how many sign changes there are. And just like we said for the positive zeros, if there are 5 sign changes, the polynomial has 5, 3, or 1 negative zeros. If there are 6 sign changes, the polynomial has 6, 4, 2, or 0 negative zeros. All right, and I might as well add to the notes real quick. By zeros, what we mean are the x-intercepts. Okay, remember when the graph crosses the x-axis, those are x-intercepts. And the x-axis is basically y equals 0. That's why we call them zeros. All right, so the x-intercepts, or the zeros, they can be negative or they can be positive. So let's look at the examples. All right, for the examples, we're going to use Descartes' rule of signs to count the possible number of positive zeros and negative zeros for the polynomial functions. All right, so let's take a look. All right, so this will be example 1. I'll just label this example 1. And here is our polynomial function f of x, and we want to find the number of positive and negative zeros. So let's start by counting the number of sign changes. All right, by number of sign changes, we mean the plus minus sign. So here, the first term is 5, okay, that's positive. All right, and when we go from positive to negative, that is 1 sign change. Okay, and if we go from negative to negative, there's no sign change there. So you can just write a 0 if you like, or whatever. You can just leave it blank. And right here, this term is negative, and this term here is positive. So that's also a sign change. All right, so a sign change is whenever it goes from positive to negative or negative to positive. So right here, it went from positive to negative. All right, notice the positive and the negative. So we counted that as 1. And here it went from negative to negative. So we counted that as 0. Right here, it went from negative to positive. We counted that as 1. So if we add up the number of sign changes, 1 plus 0 plus 1, we have 2 sign changes. Okay, and we said in the notes, the number of positive zeros it's going to be 2 or 0. Okay, you subtract an even number from the maximum and count down. It can't be less than 0, so that's it. It's going to be 2 or 0. Whatever you get here is going to be the maximum number. All right, that's going to be your maximum, and then you start with that and count down by even numbers until you get to 0. So that's it for the positive zeros. Now for the negative zeros, we have to do f of negative x. All right, let me erase this mess here so I can see my function again. All right, and for the negative zeros, we have to evaluate f of negative x. All right, f of negative x. So that means we plug in negative x in place of any x. So here we have 5 times negative x to the third. All right, use parentheses whenever you plug in negative x, and that whole thing gets raised to the third power. Minus 6 times negative x squared minus 10 times negative x plus 4. All right, so f of negative x, let's see. When you cube negative x, when you multiply negative x 3 times, that's going to be negative x to the third. All right, so this becomes negative x to the third, and it's still times 5. When you square negative x, that's going to become positive x squared. All right, and so on. So let's see. We have 5 times negative x to the third. That's negative 5x to the third. We have negative 6 times x squared. Negative 10 times negative x is positive 10x. And positive 4 is on the end. All right, just a quick review on the exponents. Let me see if I have room here. I'll just do it right here. If you have negative x and you square it, that's going to be x squared. Okay, but if you have negative x and you cube it, that's going to be negative x cubed. And why is that? Because here negative times negative is positive. Here, negative times negative times negative, because it's 3 times, is going to be negative. Okay, so this will be the case for the even exponents. It's going to be positive. And this right here will be the case for the odd exponents. It's going to end up negative. Anyhow, here is our function for f of negative x. Let's count the sign changes. All right, right here we're going negative to negative. So from here to here, the plus minus sign did not change. Right here we're going from negative to positive. So from here to here, negative to positive, the sign did change. Right here we're going from positive to positive. So from here to here, the sign did not change. All right, so we only had one plus minus sign change. And if we add the number of sign changes, that's just 1. Okay, so the number of sign changes equals 1. That's going to be your maximum number of negative zeros. All right, and now the number of negative zeros, it's going to be 1. And that's it. If we subtract an even number, we're going to go into the negatives. Okay? If we did -2 right here, we would end up with -1. You can't have a negative number of zeros. Remember, we said before, the least you can have is 0. All right? So the number of sign changes is your maximum, and if you subtract the even numbers, you're going to go into negatives. So this is it right here. All right? So the number of positive zeros is 2 or 0. And the number of negative zeros, that is exactly 1. Okay, there's nothing else. There's nothing else to count down here. So that's it. All right, please pause and try this problem here. See if you can find the positive number of positive zeros and negative zeros. And make sure you count the sign changes in the original and plug in -x and count the sign changes once again. All right, so the number of sign changes, let's see, we start right here with a positive. All right, we're going from positive to positive. So that's 0. And again, we're going from positive to positive. So that's 0. And again, we're going from positive to positive. So that's 0. Okay, and if we add up 0 plus 0 plus 0, of course it's 0. So the number of sign changes is 0. That's going to be the maximum number of positive zeros. Now, if we subtract an even number from 0, we're going to get into negatives, okay? So that doesn't work. The lowest is 0. So the number of positive zeros is 0 or none. Okay, there are no positive zeros. All right, and now let me erase this mess here. Now we're going to evaluate P of -x. All right, we're plugging in -x wherever we see an x. So -x to the 5th. As always, when you plug in for x, make sure you use parentheses. So that whole thing is raised to the 5th power, plus -x to the 3rd, plus -x, plus 4. Okay, and we said before, when you have -x and you raise it to the odd exponent, the negative remains, right? If you multiplied that negative 5 times, it would remain negative. So that's -x to the 5th. And again, the -x to the 3rd, that's an odd exponent. It remains negative. Plus -x is just -x, and then plus 4. Let's count the number of sign changes. For -x, we go from negative to negative. So right there, that's 0. Going from negative to negative, right there is also 0. Going from negative to positive, that is 1 sign change. All right, so if we add up all the sign changes, we have 1. All right, so the number of sign changes is 1. And that is going to be our maximum. So the number of negative zeros is going to be 1. Okay? If we subtract 2 from 1, it's going to be negative, and we can't go below 0, so that's it. The number of negative zeros is just 1. And the number of positive zeros is just 0. All right, this will be for the upper and lower bounds theorem. Hopefully it makes more sense once we get into the examples. But a summary of the theorem, it gives us a range of x values that contain all of the real zeros. Okay, remember the zeros are the x-intercepts. So I'll just add that real quick. X-intercepts. All right, and we can only guess what the values are and then check them. So it is very similar for both the upper and lower bounds. Okay, for the upper bounds, let's say for a positive number b, if b is an upper bound, then there is no number greater than b, that is a 0. All right, so let's say you had a number line and you had a number b, that is a 0. If b is an upper bound, then there is no number greater than b going to the right, that is a 0. Okay, and you'll see this in the example. We'll use synthetic division with b as the divisor. If the numbers on the bottom row are all non-negative, in other words, greater than or equal to 0, then b is an upper bound on the positive zeros. Now for the lower bounds, for a negative number a, if a is a lower bound, then there is no number less than a, that is a 0. All right, so we did the upper bound, and then we have 0 in the middle, and for a negative number a, so that would be to the left of 0, a negative number a. If that's a lower bound, then there is no number less than a, that is a 0. So if this a is a lower bound, there is no number to the left of a, that is a 0. Okay, similarly to the upper bound, you use synthetic division with a as the divisor. If the numbers on the bottom row alternate between non-positive and non-negative, then a is a lower bound on the negative zeros. All right, non-positive is less than or equal to 0. Non-negative is greater than or equal to 0. So for the lower bound, it has to alternate back and forth once we use the synthetic division. All right, you'll see that in the example. And finally, the starting point for finding the upper and lower bounds is to divide the constant term by the leading coefficient, both positive and negative. The positive is for the upper bounds and the negative is for the lower bounds. After that, you can work your way inward. All right, so we'll do one example of that. But if you remember, on the polynomial, the constant term will be the one with no variable, and the leading coefficient will be the coefficient on the variable with the greatest exponent. All right, so the constant term will be in the numerator, the leading coefficient in the denominator. You divide those, use both the plus and the minus, the positive and the negative, and that'll be the starting point for the upper and lower bounds. All right, first example here, example 1. They want us to show that a and b are upper and lower bounds. All right, so we have our polynomial function, f of x. We have a equals negative 5 and b equals 5. Just real quick, a is the lower, so I'm going to reverse the words upper and lower. Let me fix that. All right, so we're going to show that a and b are lower and upper bounds. All right, I'm going to start with the upper one. I think that one is just a tiny bit easier in a sense. All right, so I'm going to start with the upper. All right, and this one here will be the lower. I'll just abbreviate it L and U. Anyhow, for the upper, we're going to use both of them. We're going to use synthetic division. All right, so let's start with the 5. Use the bracket and leave enough space for 2 rows. All right, and we're going to write the coefficients make sure the greatest exponent is first and you count down one at a time. Okay, the coefficient here is a 1. Coefficient here is a 1. Negative 16. Negative 4. And positive 48. As always, you bring down the first term. That's a 1. And then you multiply. 5 times 1 is 5. And vertically, we are just adding. 1 plus 5 is 6. 5 times 6 is 30. Negative 16 plus 30 is 14. 5 times 14 is 70. Negative 4 plus 70 is 66. 5 times 60 is 300. And then 5 times 6 is 30. So this is going to be 330. And adding this is 378. Now, these are all positive, or should I say they are all non-negative. Let's check the notes real quick. Using synthetic division, if the numbers on the bottom row are all non-negative, in other words, greater than or equal to 0, then B is an upper bound on the positive zeros. So what do we have here? These are all non-negative. Okay, that means they are greater than or equal to 0. All right. So therefore, these 3 dots, that means therefore 5 is an upper bound. And I think I drew my inequality wrong. I wrote it less than or equal to 0. No, that's incorrect. Okay, non-negative means they are greater than or equal to 0. All right, so in other words, 0 or positive. All right, now I'm going to erase this, and we will try the lower bounds with negative 5. So I'm going to use negative 5 here. All right, we did the upper bound of positive 5. Now we're doing the lower bound, which is negative 5. Okay, the coefficients are the same. The polynomial function is the same. So we have 1, 1, negative 16. Negative 4 and positive 48. All right, so same function. Bring down the 1. And let's see, starting as always, negative 5 times 1, that's negative 5. Adding vertically, 1 plus negative 5 is negative 4. Negative 5 times negative 4 is positive 20. Negative 16 plus 20 is 4. Negative 5 times 4 is negative 20. Negative 4 plus negative 20 is negative 24. And let's see, negative times negative is positive. 5 times 20 is 100, and 5 times 4 is 20. So we have 120 right here. And 48 plus 120 is 168. All right. It looks to me like the numbers alternate. Positive, negative, positive, negative, positive. Let's check the notes once again for the lower bounds. All right, so for the lower bounds, when you use synthetic division, the bottom row has to alternate between non-positive and non-negative. Okay, so non-positive is less than or equal to 0. Non-negative is greater than or equal to 0. And if that happens, then A is a lower bound. Okay, so let's check it out. All right, so just like it said in the notes, the numbers on the bottom row here, they alternate between non-positive and non-negative. All right, this is non-negative, non-positive, non-negative, non-positive, and so on. Okay, so these alternate. between, let's see if I have room here, non-positive alternate between non-positive and non-negative. All right. Therefore, -5 is a lower bound. All right, so that's it. All right, please pause and try this one here. I want you to prove that -5 is a lower bound. And I'll give you a hint. The number 0 is both non-positive and non-negative. All right, synthetic division, -5 out front. Make the bracket to accommodate 2 rows. Coefficients are 4, 20, 7, 3, 6. Make sure the exponents count down by 1s with the greatest exponent first. All right, so 4, 20, 7, 3, -6. Okay, and we are adding vertically as always. All right, bring down the first term and multiply. -5 times 4 is -20. Adding, that's a 0. -5 times 0 is 0. 7 plus 0 is 7. -5 times 7 is -35. Adding, that's -32. And let's see, negative times negative is positive. 5 times 30 is 150. 5 times 2 is 10, that's 160. And adding, that's a 154. Now we have a 0 here. Remember the hint at the beginning. I'll write it here. 0 is, I'll abbreviate it. 0 is non-positive and non-negative. Okay, 0 happens to be both. So we said in the notes, for the lower bound, it has to alternate on the bottom row. So this is non-negative, non-positive. All right, 0 is not positive. Non-negative, non-positive, non-negative. Okay, they alternate. Therefore, -5 is a lower bound. All right, that's for the zeros or the x-intercepts. It doesn't go below -5. All right, so last one, let's try this example. What is the starting point for the upper and lower bound? So we have this function here. Let's look at the notes again real quick. We said the starting point for finding both the upper and lower bounds is to divide the constant term by the leading coefficient, both positive and negative. The positive is for the upper and the negative is for the lower. Okay, so let's try that. All right, so pretty simple. Please pause and try it real quick. You're going to divide the constant term by the leading coefficient. All right, so the constant term is the one with no variable. That is positive 50 in the numerator. Actually, we need to worry about positive or negative because we're doing both plus and minus anyway. And the denominator is the leading coefficient. You look for the greatest exponent. The coefficient is 2. So, of course, 50 divided by 2 is 25. And that's plus minus. All right. So, in the examples, I believe we use B as the upper bound and A as the lower. So, A is negative 25. And B is positive 25. All right, and that is the lower and the upper. All right, so basically, if you had to keep going, you would be on the number line, and you'd have 25. And you'd have negative 25. Okay, so you wouldn't try any numbers. If you kept going, you wouldn't try any numbers to the right of 25 or the left of negative 25. You would basically work your way inward. So those would be the starting points for the lower and upper bounds.